Hello and welcome back to the second installment of this review of my 6502 ASM solutions for Advent of Code 2023. So today we're going to look at day 1, and I have the text on screen already. Right, so we can see here that we have an input that is lines of text. Each line has a value that we need to recover. Each line has a value found by combining the first digit and the last digit in that order to form a single two-digit number. So we can see that sometimes we have one number at the beginning, one number at the end. Sometimes we have just two numbers somewhere in the line. Sometimes we have more than two numbers. And sometimes we have one number which becomes two numbers, right? It's the first and the last, that single number. So we can't have zero numbers. That's probably a good point, a good thing to keep in mind. So with that in mind, let's go to the code. Let's minimize this and let's have a look at what's going on in here. So in my solution, we start our code. What do we get? We pick the counter that I'm using, which will be counter 1 for part 1, right? Then we store the max range, which is the size of my input. Apparently my input is 54C8 in size, which probably comes up to about 22 kilobytes. That is the size of the file. And then we zero out these values here in memory addresses 15, 16, 17. So memory address 15 is the first digit found, which is the tens column. Memory address 16 is, I have here updated each following digit found. So every digit that is found goes into 16 in order. So the last digit should be in there, right? And 17, I'm storing a check to see if any digit has been found, right? The first digit has been found, essentially. Now, I think essentially I don't need this 17. I could have just used 15. So that's a mistake or a inefficiency in my code already, but that's all right. Next, we're storing the address of all the input, which we get with this little pointer here, inputs, and the low byte by this less than sign goes into memory address 10. The high byte goes into memory address 11. And so we set up our counters, these registers X and Y to zeros, and here is our loop, our reading loop for reading the input. And when you have a memory address in brackets like this, it treats it as a memory address. It treats the value inside as a memory address. And so it uses that address as the low address and the next address, which is 11, as the high address, and uses Y here as an offset. So Y starts at 0, and this is really good because the way you have this 8-bit value and these 16-bit addresses, let's say the memory address for input starts at, I'm just going to put a random number here, 1012, right? So 102, 8012, with an offset of 0, of course, 8012. But when that offset gets up to, say, 255, right, it's essentially pointing at memory address 8111. Okay? So, I mean, what do you do now? Well, all you have to do is increment that high level address, this one here, in 11, and then you can start again from 0. Right? If you increment y to there, to 81, x can, the address in 10 can stay at 12, y resets to 0 as it rolls over, and you can just keep going. And it's a very nice, simple way you can keep looping through a large input block, a large block of data, until you get to your desired, or to the endpoint, effectively. You don't really have to keep track of like when you might have to change your offset or anything like that. It's just the offset keeps going, counting up to 255, and then you increment the high byte, and then you just start going from 0 again. It's very useful. Very, very useful. Let's get rid of these. You know what? I shouldn't have done it that way. Doesn't really matter. Whatever. So, but in our loop, the first thing we do is this load. We load the byte from the memory address in the offset and compare it with 0 for the null character. If it's a null character, we evaluate the line, right? We should have values in 15 and 16 already, so we can evaluate it to see what the number was and add it to the result. Otherwise, we put the value into 14. We keep a hold of it for later, and then we check to see if it's a letter. Now, since it's ASCII, any values that are above, say, I think it's about 40 hex, are not digits. And in this case, using C0 here, you get the top 2 bytes. All characters will give you, all non-digit characters will give you a result greater than 0. So if it's not equal, right, it's not equal to 0 effectively, we'll jump to increment menu, increment the memory. Otherwise, we load that value back out of 14, because the A register after this AND would be either 0 or some value compatible with C0. We load that value back out of 14, and we AND it with OF. So the digits are something like 30 hex to 39 hex. ANDing it with OF easily gets rid of the top area of the hex value, giving us just the digit. Just the digit value in hex. And so we store that into the last scene space, 16. Right. And then we load 17, and we look to see if it's above 0 by ANDing it with FF. You can do a compare. I'm not quite sure why I decided to do AND FF instead of comp 0, 0. It may just be that, well, AND FF might be a little bit faster, might be a clock cycle faster. Regardless, it works if it is not equal to 0, so if it's greater than 0, then we go increment the memory. Otherwise, we load that 16 value again, and we store it into 15 and 17. So that's basically, this was the first digit we found, put it into the tens position. And then we go to that increment menu. So let's have a look at that increment memory. So we increment the Y counter, and then we check if it is 0, 0, if we have rolled over. If we have rolled over, then Wait a second. If we have, right, not equal, yeah. If we have not rolled over, right, then we check to see if we've reached the end effectively, right? We check to see if y is the offset required for the end of the file, and we check if x is the length we need for the end of the file, end of the input. Basically the high byte and the low byte are the right values. If they're not, then we go back to the loop. If it has rolled over, then we increment x and we increment the value that's in 11, which is that high byte from the memory address for our input data. So then what's left? Our eval line. So we've gone to the end of a line. We've got some values in 16, 15, 16. Now we need to add them to, well, sum them to our output, our result. So firstly we store y, we back up y because we're going to use it. Clear our carry, load y, load a from our counter. The last value, the ones column, we add the value of 16 to it, which is the ones place. We store it back into the counter. Right. Then we we set the carry, I think. Yeah, we set the carry flag. We load a 09. We subtract the value of that, the ones column, from 9. And if we are positive, so if we've subtracted a value less than 10 from 9, we end up with basically 0 to 9, right, as the result. If we're positive, then we jump to this one here, adding the tens column. If it's not positive, it's negative, right, then the value that we've got in the ones column is above 10. So we load it, we subtract 10 from it, right, which is hex A, we subtract it, we store it back, and we increment the tens column, which may increment the hundreds column, which may increment the thousands column, which may increment the 10,000s column, right? It will shuffle along if it needs to. And then we fall back into the adding the tens place. Basically the same thing. We clear the carry, we load the tens position and the value in the tens column, add the value of 15 to it, and then we do that whole check again. Only would finish the evaluation if it's less than 10 in the tens column. Otherwise, subtract 10 and increment the hundreds, etc. And then we finish the evaluation. When we finish the evaluation, we clear out the values in 15, 16, 17 and bring back the value of y. And then we fall into incrementing the memory. Right? We fall straight into incrementing the memory. We don't return to the subroutine or return from the subroutine. We just fall into incrementing the memory. And so it just goes through that all the way through the input. So that's part 1. That's how part 1 works. What about part 2? So let's first open part 2. And then we'll look at part 2's code. Part 2's text, actually. So we'll look at part 2. What have we got here? Now, calculation isn't quite right. Looks like some of the digits are spelled out with letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. Also count as valid digits. Oh no. What do we do now? So we look at a new example input. Right, 2, 1, 9. We have a 2 and a 9 there. 8, 2, 3. Oh, 8, 2. See, you can see we have 8 as a valid word there, and 2 is a valid one there, and 3 is a valid one here. Now this caused all kinds of problems with some people, some solutions. Right. The biggest problem would have been if these two are like this, with no 3 on the end there. So a lot of people did replace, so they replaced 8 with a digit 8, and that replaced the T, and so it wouldn't match 2 anymore. And so you just wouldn't get the right number out. Not sure if there's actually one in here that has that. Nah, not in the example. But still, yeah. There are 1 and a 3 over there. Yeah. So we're looking for words. Looking for word strings that match the digits. So how did I do that? Well, let's go back to the code, shall we? Let's go back and have a look at the code. So everything's else basically the same. Start part 2. We choose pointer 2 this time. We want to store it for part 2. The result in part 2. The starting all the same so far. Let's go down. The first difference, I have this do eval. It's a little bit different from the last one. We still... Oh no, I think actually the do eval is probably the same. I think the only real difference here is this shuff buff. Right, we have this branch not equal to shuff buff. So if it is greater than 0, we branch to the shuffle buffer. Rather than branching to incmem, incrementing the memory, we branch to the shuffle buffer. The rest of this is still the same. And then if we have a number here, we branch. If it's not the first time we found a digit, we branch to the shuffle buffer. Otherwise, we fall into the shuffle buffer. Right. So what is our shuffle buffer? What is this? Well, let's go down a few lines here, shall we? Here we go. This is all my shuffle buffer is. So for some reason I'm loading the value from memory address again instead of using 14. To really just have I should really just have, and what do I have here? What was it again? Should really just have 14 here because I would have had it in 14 anyway. It was saved a couple of frames, and I store this into 65. Right. Back up Y to 1D. Now load 4 and this is going to be my memory offset. 4 into Y. Now load the value of 60 plus the offset of 4. So 64. Now I store it into 66. Now I load the value of 65, which was the value that just came from the input, and I store it into 64. Now load the value of 66, which was the value that was in 64, and I put in 65. Right. Then we decrement Y, and we go back to the top. So now I'm loading the value that's in 63, and I store that into 66. And I load the value from 64, which is in 65, I put into 63, right? And so I'm just shuffling values along this 5 bytes of memory. And then once that's done, we go to this subroutine called check words, which is another new subroutine. So where is check words? There it is down here. So now I'm checking that buffer from 60 to 64 to see if we have a word in there. I'll start off with the 5-letter words. So this one here, I'm checking to see if the value is 3. Is the word 3 in this 5-letter buffer? 5-character buffer, right? So firstly, I'm checking to see if it is a T in the first space. If it's not a T, we just branch off to the 7. Check to see if the word is 7, right? Clearly not. If it's not a T, it's not going to be the word 3. If it's not an H in the second space, branch to 7. If it's not an R in the next space, branch to, right? Each time it's not the right letter, we branch to check the next word. So on 7, right, we're checking if we've got an S, otherwise we branch to 8. Once we're in 8, we branch, if it's not the right letter, we branch to check if it's 9. Right. And so from 9, we're starting from position 61 because 9 is only 4 letters long. We only want to check as the word comes into the buffer. So we don't want to check if there's 9 from positions 60 to 63, because once 9 comes in, then we'd have to either clear out the buffer or we'd have to somehow ignore it really gets shifted along one more place. So yeah, we only check it, we're only checking like once, as soon as it can be in the buffer sort of thing. So let's start from 61 this time, and any cases where it's not, we'll jump to the next one, which is 4. This one here, if F is not the first word, it's not going to be 5, right? It's definitely not going to be 5 in there if F is not the first letter. So in this case, if it's not an F in the first place, then we jump to the 1 check. But the rest of them will jump to see if it's 5. Right, the same with 5, we're jumping to see if it's 1. We don't have to check, if we get to 5, we don't have to check the first position anymore because we know it's an F in there. So we only have to do 3 checks. Then we check 1. If it's not 1, then we check 2. If it's not 2, we check 6. And if it's not 6, then we branch to go back. It's down here. Our return to subroutine. But if we get to the end of any of those and it's a digit, it's a valid digit has been found, then the value of A will be that value. So we'll store it into 16. We check to see if it's the first time a digit has been found. If it isn't, then we go back. But if it is, we put them into 16, 15, 17. The same way we're doing it before. Right? And then everything else is the same. And that's how I checked 4 words in the in part 2. So let's see if it runs. Let's see it run. Let's go to Messen. Here's Messen. Got Messen running. So I'm going to press A and we're going to watch this thing run and spit out the correct result. Actually, let's bring up the correct result as well, shall we? Let's have a look. Alright, now you can see the correct result on screen in the browser window, and we're going to run this. Takes a couple of seconds to get there, and yes, there we go. The correct result. Very well done. And I suppose I could even bring up the memory viewer so we can see the results in memory. see. Oh, here we go. Here we go. I'll just capture another window. Here we are. That's the one I want. Bonk. And there we go. You can see in this area in 400. Oh, it doesn't make that any bigger. Let's make this any bigger. Bonk. You can see here in memory we have the result stored from 400 and 407 to 40C. Alright, so, and there's it going nuts as it does because it's checking the thing constantly. You can even do, here's a fun thing to do as well, one more little show. Let's see if I can run this again. Bonk. Nice. Well, that might be fun, actually. Let's slow it down. It's got half. And we can see in this area here in 60, you'll see my shuffle buffer going nuts. And you'll see over here the contents in ASCII. Let's run it one more time. It's still too fast. Yeah. Alright. Anyway, so that's my solution for day one. It was a fun little day. Didn't take that long. It still took, it took quite a while for the 6502. But I did get it done within the first day. So it took me a few hours. Alright. So, that's it for day one. I hope you'll be back for day two.